Much for the wonderful introduction, Rajiv, and for the invitation and all the great vision that went to this workshop. He gave me a little bit too much credit. It was mostly his idea and his energy to make this all happen. So, again, thanks everyone for making this happen and providing this opportunity. I'm going to be talking about a topic specifically on trustworthy computations on untrustworthy systems. This work I'm going to present was in collaboration with several PhD students, shown in the first two lines here, as well as several other faculty members shown on the last two lines in this list of collaborators. The problem I'm going to talk about is actually very simple. I have this computer here that I'm right in front of me, and for all I know, I think it's presenting this slideshow. However, how can I, as a person, really know whether my computer is secure? Or how can I know what is currently executing on this machine? It's definitely presenting these slides, but in the background, this processor that runs at over 2 gigahertz could be doing a lot of other things as well. It could be sending spam email to all of your inboxes right now. It could be launching a denial of service attack as a host in a botnet, etc. So as a user of these machines, it's very difficult to be able to determine what these computers are actually doing. So if you look at this, this is especially a problem when you start doing security-sensitive operations. So for example, you want to perform a bank transaction. How do you know that what you see on your screen is actually what's going on? Because there's new malware called transaction generators that utilize your login into your bank account and then behind your back inject malicious transactions and then send your money to some other bank account. But whatever you see on your screen is what you're expected to see, and you have absolutely no idea what's going on behind the scenes. So the question I'm going to address in this talk is how can we achieve higher assurance for our operations that we perform, be it on our laptops or being on mobile systems, handheld devices, cell phones, or also in the cloud environment. Right? As we're sending our computations to some server that performs this computation for us, how can we obtain assurance that the server is performing the correct operations and is not stealing our information? So essentially, the central message I'm trying to convey here is there's an approach called trustworthy computing. And these new computing mechanisms enable fundamentally new properties to achieve assurance in a variety of systems, mobile system or cloud computing systems. So specifically, on a host, on a computer, these new computing primitives enable protection for code and data, even from the administrator who is the main user of the host. Even for the person who has all administration privileges, you can actually protect data from them and provide secrecy of that information that, again, even the main administrator cannot steal that information. You ask, how can this be possible? Well, I'm going to tell you one approach how this can be achieved. And also in distributed applications, you'd like to obtain a data verification based on the code that produced it. This is actually a very powerful concept. And I could have a whole other hour lecture how to apply this concept to design secure systems. In fact, if you know this piece of code has produced that piece of data, you get very strong assurance for that data that was being produced. It may sound very simple. However, this mechanism allows you to very easily use very sophisticated cryptographic techniques can accomplish in this case. And finally, we'd like to achieve very strong assurance to the human user. I won't be talking too much about this in this talk, because that's a whole other set of complexities that come into play. How can the actual user gain some strong assurance? However, that's one of the underlying goals of all of this research. And so finally, again, these trustworthy computing mechanisms I'm going to present, they provide new primitives to build secure systems. So I'm going to start out by introducing the isolated execution environment. So I'm going to depict current computing systems based on the following diagram. where we have at the bottom we have the hardware that the system relies on, for example, DMA devices, like network disk, USB. DMA stands for direct memory access. This can actually access arbitrary parts of memory. That's a challenge because your network card or your disk or your graphics card could be malicious. Right? And in fact, we've already seen malware that infects your network card, and then from the network card affects the remainder of your operating system. We then also have CPU, RAM, TPM, and I'm going to talk more about the Trusted Platform Module, or the TPM, in later slides, and the chipset of the computer. We then have the very large operating system, and the size depicts also the complexity of these different components. And current operating systems are truly complex because they have several millions of lines of code. In fact, tens of millions of lines of code. We then have applications executing on top of the operating system that are usually a little bit smaller in size. However, even a browser today has millions of lines of code. I'm emphasizing on the size of code because the code size corresponds oftentimes to the number of vulnerabilities in the system. You have some estimates say per 1,000 lines of code, you have one security vulnerability. That's a big problem if you have millions of lines of code, right? Because you're expecting to have thousands, if not 10,000s of security vulnerabilities, some of which are found every few weeks, right? And new ones are discovered over very long time periods. Now, this color coding indicates that red we don't want to trust. Right? Ideally, if we want to execute some security-sensitive code S, and that's shown in blue here, we don't want to trust the operating system, or we don't want to trust device drivers or DMA-based devices in your system, or other applications, because you would have to trust way too much. And so ideally, you only have to trust a very small component of your system, and that's shown in green here, which is the CPU itself, the memory, this chip I'm going to talk about, TPM, as well as the chipset that handles interactions with memory and some other devices. So you do need to trust that they operate correctly. Then the goal I'm going to present is that we can execute code S in complete isolation from everything else on current computing systems. So that we can start to hope that we can achieve some security properties for S, because we can rule out trust in all these other components of your system. In fact, to further motivate this issue that operating systems have many vulnerabilities, I just got this email 2 days ago from CERT, which is actually in the same building at Carnegie Mellon University as Scilab is in. They oftentimes send out these advisories about security vulnerabilities that were discovered. And I got this email here that discussed a new set of security vulnerabilities on Microsoft products. It says affected our Windows, Internet Explorer, etc., with multiple vulnerabilities in these systems. And then here in red, what it said is remote, unauthenticated attacker could execute arbitrary code, cause denial of service, or gain unauthorized access to your files or system. So this is very serious, right? What this means is that if you have such a computer system, an attacker can exploit these vulnerabilities to then execute code in your system. They can install software that waits for you until you log into your bank account and then inject transactions that you try to perform on your bank account. So this is a major problem. And I don't want to talk about Microsoft here because everybody has the same issues. It's not that Apple is more secure. It's just that there still are more Microsoft computers, so attackers predominantly attack Microsoft, but Apple or all the other ones are in no means more secure. They have the same complexity in code size. And of course, there are some differences. However, overall, if you search, almost any system has security vulnerabilities. But this is just to illustrate that we don't want to trust operating systems or browsers that contain millions of lines of code. And so in this talk, I'm going to come back to this slide, describe mechanisms that allow us to isolate execution of some security-sensitive piece of code from all the remainder of your system. So you don't have to trust the operating system. You don't have to trust the administrator that handles the whole machine. So now I'm going to make a few assumptions for this talk. In fact, we're going to have a verification device, or a verifier. And the first assumption is that the verifier has the correct public keys to validate the attestations that I'm going to be discussing. This is important because key distribution is a whole other area that I won't have time to address in this talk. I'm also assuming that the actual hardware that was shown in green, the processor, the memory, the chipset, is actually secure. Specifically, there's also a special mode in a computer called SMN mode. And I'm also going to simply assume here that that is secure. And I'll be happy to discuss with you what we can do if there is malware in that part of your computer. Also, another assumption is that isolated code itself does not have vulnerabilities. So that was this little piece S that we want to execute. And the assumption is that S is relatively small for most security-sensitive operations. We're not, on a first approximation, we're not going to run all of Microsoft Word inside S. Because we don't know yet how to really prove security for these very large-scale systems. We only know how to prove security for much smaller systems. And that's, I'm going to make that assumption for the remainder of this talk. So, briefly, two observations, which is trustworthy computing actually does not try to prevent a sophisticated local physical attacker. Because that's a whole other level of security that is necessary to accomplish security against a powerful local adversary. However, we do want to prevent remote attacks, and they represent the vast majority of all attacks in today's internet. And so I've also been talking about protecting against a malicious administrator, and here the assumption is the administrator doesn't actually perform a hardware-based attack. Right? The administrator performs purely software-based attacks, which I'm going to show how we can prevent. Now, I'm going to start out by showing what mechanisms industry has provided us to accomplish these properties. And we're going to specifically discuss how we can actually create such an isolated execution environment on a current platform, and also how to remotely attest or how to remotely validate this isolated execution environment. I'll then also briefly discuss how we can inject secrets from a remote host into this isolated execution environment in a way that the local administrator cannot attack or obtain the secret. And finally, achieve the property that some output O was truly generated by this code S and computed on input I. But before I can go and discuss these in more detail, I need to discuss the Trusted Platform module, which is a new piece of hardware that the computer industry has designed to accomplish some of these properties. So specifically, globally, a lot of the computer manufacturers, or pretty much all the major computer manufacturers, have collaborated to create a standard as part of this trusted computing group, to the standard for a trusted platform module. And that's an extra chip that today 500 million computers already have. So the deployment is already very widely accomplished today. I'm going to assume simply that this TPM chip has a public-private key pair using public-private key cryptography. And I'm also assuming that there's actually a manufacturer's certificate that authenticates the public key of the TPM chip. So if you want to communicate with another computer, you would obtain a certificate saying this is a valid IBM computer, for example, with an IBM signed, an IBM-based signature on the public key of that TPM chip, for example. And there are a lot of details that I'm glancing over here, but this high-level understanding enables us to see and understand the property that the system can provide. Also, there's no active tamper response though in this chip. Again, it does not survive sophisticated local attackers. It essentially only is against relatively unsophisticated local attackers, but still, this is a huge step forward in achieving secure systems. So now the first question is, how can we actually create this isolated execution environment? Because you have if you think about it, it's a very difficult challenge. You have a computer system with all its BIOS, the whole operating system, that executes. Millions of lines of code that have already run on the system. So the question is, how can we bootstrap a small piece of code that then executes in complete isolation from all this other stuff on your computer? Right? You have, and so fortunately AMD and Intel came to our rescue to accomplish this task. They have created a new instruction in their processors. And AMD called this instruction SKInit, or secure kernel init, and Intel called it secure enter, or senter. But the instructions are essentially equivalent. They just had to call them different names to make things more interesting for us. So these instructions are very powerful. They're essentially, if you're a security person, they're the answer of Friday, Christmas, and Easter, a huge gift, all at the same time. It was like a gift passed to us, because what these instructions do is they create an isolated execution environment by essentially resetting the CPU. It's a soft reset, and then essentially isolating all the exceptions and interrupts from executing, so that the next piece of code that's going to execute cannot be interrupted by any code that was there previously. So it also enables DMA protection for the entire secure loader block. This is, again, very powerful because a lot of devices on your system that you don't need to trust have DMA access. So this prevents, for example, a malicious network card from being able to read or overwrite the code you're currently executing. Again, this is tremendously powerful because a lot of attacks can simply operate by somebody plugging in a malicious USB device, or especially over FireWire, you have full DMA access. Without this protection, somebody, I call this the cleaning lady attack, they can just simply connect via your FireWire port, and within fractions of a second, compromise your entire operating system. They just plug in this device via FireWire, they can read out the cryptographic keys in your operating system within milliseconds, and within milliseconds write malicious code directly into your operating system space that then can execute. So it takes less than a second to compromise a host using these type of attacks. And now these new properties of these instructions prevent these type of attacks, because the code that you're going to execute next is completely protected from any of these accesses. Then the next property is that the secure loader block is being hashed, and that hash is being sent to the TPM chip that then can prove to an external party that this code has truly executed. And also then the processor actually finally starts executing this code. So essentially, to look at it, it's as if you take a vault, and you want to execute this piece of code, you place it inside the vault for execution. And you isolate everything that happened previously from that code. Now the next question is, now that we know how to run code in isolation from everything else on your system, how can you prove to an external party that you actually have performed these operations? And that's another important question, because there could be malware on your system that simply virtualizes and claims to have executed these instructions. Right? You could have a piece of code that says SKInit or senter, but then the malware, which has, for example, root privileges on your system, detects that it's trying to execute this instruction and simply does not execute it. Simply pretends as if this instruction had executed. So the question now is, how can we really obtain strong assurance from an external verifier, shown with a V here, that the computer actually produced or performed SKInit and has now created this secure execution environment for security-sensitive code S. And so in the middle you see the actual computer system, and on the right you see the TPM chip with S. Of course the TPM chip is part of your computer system. Just conceptually, I show the three parties separately here, where the verifier will be an external device, such as a cell phone that can validate the execution on your computer, or another computer system altogether. So to obtain freshness of the response, V is going to send a random nonce n to this computer system, which essentially then calls SKINIT and executes S and passes this nonce at the end to this execution environment. Now the TPM chip is going to digitally sign the hash of S and this nonce n, which is shown here with this gray box. So the gray box indicates a digital signature with the private key. And simply the computer system can pass this information back to the verifier that can then validate and ensure that truly SKINIT and SENTER have executed and that this is a new response because the nonce is included in the signature. And I'm going to show this with a little bit more detail when I talk about the system we've built based on these instructions. The next question is, how can we actually establish a secure channel with this security-sensitive code? So externally, as this trusted party V, you, for example, want to inject some secret into this execution environment. And the way this can be accomplished is that S, as part of this execution, produces a public-private key pair shown here with K and K-1. And it then also attests to the public key K that is included in the signature and passed back. Now when V receives the signature on the hash of S and the public key K, V obtains assurance that it's truly S that has produced this public-private key pair K and K-1, and that because of the isolation of this environment from everything else in your system, V knows that the secret or the private key K-1 is truly a secret. Because even an administrator could not have obtained K-1. And the reason is, let's say the malicious administrator wants to obtain key K-1. It would say alter the code S to send the private key out to an external entity. Right? But if you do this, the code itself will change. Because the original code S does not have the capability or does not have a functionality to send out this private key K-1. Therefore, if the administrator tries to change S, it's going to become completely obvious to the external verifier that S has been changed because the hash value of S will be different. So you can immediately tell that some malicious operations are happening. So now that the verifier knows that this public-private key pair was produced securely and that code S truly has executed, it can now encrypt some other secret using the public key K and send that back to the system, which then passes it on to the TPM protected information that then essentially can decrypt the secret value. So finally, the last property is how can we assure that the code S has truly produced output O based on input I. And similarly to what I showed just now, these same primitives enable verification that the code S has truly executed within this isolated execution environment. So these are the very high-level concepts. And next I'm going to show how we've built the system based on these properties, or based on these primitives I've shown, to achieve these properties I've just discussed. And specifically we built a system called Flickr. And the main students on this were Jonathan McHugh and Brian Parno. Arvind Seshadri also helped, and Mike Ryder was another faculty who collaborated on this project. And the main goal of this Flickr project was to obtain essentially that last property I've just shown. To obtain isolated execution of some security-sensitive piece of code S, and to obtain an attestation, so to enable a remote verifier to validate that the code is truly executed in isolation, and also achieve a minimal trusted computing base. So the trusted computing base is everything that you need to trust for a given security property to hold. And we'd like to trust as little as necessary. We don't want to trust tens of millions of lines of code of Windows, or tens of millions of lines of code of Mac operating system. The color coding I'm going to use to illustrate this is red means untrusted, green is the trusted part, and blue is the verified part. And so you can see in this diagram that we only want to trust the hardware. The verifier itself is trusted as well. And then we're going to have a small shim layer that is essentially a tiny micro-operating system to execute our security-sensitive code S. So this is part of this Flickr system that we've built. We built this small shim layer that is essentially only 250 lines of assembly code. So that you need to trust. And you also need to then verify your security-sensitive code S. But the shim layer, as I'm going to show, is actually verified as well. So you don't axiomatically need to trust it because you will obtain assurance that the shim layer has correctly executed. So here's how Flickr works in a little bit more detail. So we have some application that wants to execute, and now here green means that it's executing. So the application wants to call some security critical code S. And what it does is it first calls our Flickr module that is actually part of the operating system. And the module first essentially stores a snapshot of the current execution state in RAM. It then calls this SKInit instruction on AMD CPUs. And as I said earlier, SKInit micro-reboots your processor. So essentially it erases all the execution state that was present. And so the whole operating system, for all practical purposes, is out of control. It cannot gain any additional control. Then the CPU also resets part of the TPM chip and then starts executing our shim layer. This shim layer then executes S, and finally, when S is done, it returns control to the shim layer. These 250 lines of code essentially reconstruct the execution state to send control back to the operating system after the security-sensitive operations were performed. Now, I glanced over a few details based on what happened with this TPM chip, because that's going to be essential to prove the properties to an external party. And a little bit more specifically, what has happened is the TPM has some special registers. They're called platform configuration registers. They essentially store state about your execution environment. And initially, those registers were 0 because the SKInit operation actually reset these registers. And then the hash of S and the shim layer was sent to the TPM chip. So this TPM chip stores that hash value, and after execution ended, a stop value is being stored there. So that you can distinguish what happened before and what happened after the execution. There's another of these registers that stores the hash of the inputs and the hash of the outputs that were produced, and again the stop value, so that you can externally verify exactly what happened during this isolated execution environment. And now this key, the TPM's private key, KMS1, is used to attest this state to an external verifier. So the external verifier can, for example, ask, what code did you execute? And the TPM will digitally sign its platform configuration registers, which encode the hash of the code as well as the inputs and outputs. And so now the verifier obtains exactly this property that on this computer system, this specific piece of code has executed in isolation on the input and produced these outputs. And maybe some people may be familiar with the older type of platform attestation. That was the first approach that corporations tried to achieve strong properties on applications, where essentially the hash of every single executed piece of code was stored in the TPM chip. So essentially every device driver, every kernel module, every application that you execute, the hash is stored on the TPM chip, and then the TPM chip can sign what has been executed. So the verifier, if the verifier wants to obtain assurance of this system, the verifier will check that no malicious code is executed. So that's the assumption here. So it has all the hashes of everything that has executed, and the verifier will check that it's happy with all that code that has executed. But again, you have millions of lines of code that you're attesting in this way, that you're checking in this way, and essentially can get no strong security properties because absolutely a lot of this code has vulnerabilities, and you don't want to trust it all. So the trusted computing base of the top Flickr-based approach is really tiny. You only verify on the order of a few thousands of lines of code instead of millions of lines of code. Now, let me show an application of this approach to SSH passwords. So here the problem is, when you have a computer and you want to log into a server via the SSH protocol, essentially what happens is you send your password, if you use password-based authentication, you have to send your password to the server, to the server's process that's running your SSH daemon. And this is a problem because a malicious administrator could easily replace the SSH server program with a malicious piece of program that not only checks your password correctness, but also stores it in a file. So whenever you log in SSH into a machine, you're actually trusting that piece of code, that that piece of code does not steal your password. It only verifies it, doesn't store it. And so based on what I've just shown, we can obtain a much stronger property. So the way to accomplish this is the system where you're currently typing in. So this is now the computer system, and you trust your local host, and you don't trust the server. You send a nonce to this server, and the server essentially opens up a Flickr session, executing a small piece of code that is going to validate your password. And that's again this code S with the small shim layer. And this generates a public-private key pair, and it also needs to store state, because Flickr can only run during a very short time period. So it then performs an operation I haven't really explained it, called sealed storage, which essentially binds a secret to a hash value so that the operating system cannot obtain it, but the TPM guarantees secrecy for this piece of code. Then there's also an attestation that is being produced so that the client can obtain a public key K and an assurance that S is correctly executed and the assurance is also on the public key K and on the nonce. That's not shown here, just to keep it simple. The client then knows, okay, I can trust this piece of code S because you can inspect it yourself, and you can then encrypt your password using this public key K, and then when this is being sent back to the server can again invoke another Flickr session and pass it the sealed storage part here shown again in this gray box, that then the security sensitive code can decrypt, again while it's in isolation. And so using this private key K-1, it can then decrypt the password, check the password, and send back an OK message to the operating system. So notice that all these operations shown in red here happen within this isolated execution environment. And notice now that a malicious administrator cannot obtain access to this password. And the reason again is because the client computer checks what code can check my password. And you can inspect it, you can see this code does not steal my password. And so therefore, you can then obtain very strong assurance that even a malicious system administrator could not obtain any assurance, or could not obtain your password in this way. Now, one issue with Flickr is that it's actually very slow. It takes a long time to execute this skInit function every time you want to execute something. So we've created a more efficient system called TrustVisor, which essentially uses the following trade-off. It increases the size of your trusted computing base, but it provides much higher efficiency. And in order to save somewhat on time, let me just briefly explain this. I'm not going into too deep detail, but essentially the difference is that we implemented a small hypervisor that's a small piece of code that executes essentially underneath your operating system. And it then virtualizes part of your computer system that is required to obtain a strong security property. So it essentially virtualizes the memory controller in order to being able to protect memory in a way that even the operating system cannot access that area of memory. So the way TrustVisor operates is some application now contains the security-sensitive piece of code S. And the application can register S with TrustVisor And then this piece of code essentially becomes blue because TrustVisor protects it from the whole remainder of your system. So S now can be essentially called by a regular function call, but whenever it's invoked, TrustVisor will change the memory permissions to enable execution. Whenever S returns, TrustVisor will re-enable protections on that memory area so that the operating system or even the application itself cannot access those memory locations. So we've also implemented a micro TPM chip within this framework that then offers much faster sealing, unsealing, and digital signatures on the current execution to prove execution to remote verifiers. So this now looks very similar as the previous slide. However, when you now verify what code is executed on the system, you essentially also get a proof that TrustVisor is executing correctly. So what has happened here, we've increased the trusted computing base from the 250 lines of code of Flickr to roughly 5,000 lines of TrustVisor, but we obtained much higher efficiency of the system. So I'll now show briefly another example of the system that we've built, which is the Apache web server that wants to open up or be an SSL-enabled web server. So it has a public-private key pair for the SSL operations. The goal we want to achieve is that no system administrator or no malware can access the private key for SSL. So that's this K-1 for SSL. Because we know there are a lot of ways in which this private key could be stolen, for example, through malware that infects your system, and then it can steal your private SSL key. Certificate of location isn't that easy to perform, so you absolutely want to protect that key in a way that it cannot be exposed to malware. Also, you don't want to trust the administrator who handles all your web servers, and you want to protect this key even from those potentially malicious administrators. And again, you want to provide external verification of this entire setup. So we've implemented two security-sensitive code modules S that essentially, the first one generates this public-private key pair, and the second one essentially then uses the private key to open up SSL connections. And this is in this tiny piece of code S that runs then in isolation from your entire Apache web server or your Linux operating system. And here I briefly show some experiments showing that the efficiency is very high. This shows the number of transactions that could be performed compared to standard Linux. So standard Linux without TrustVisor and without any protections runs at speed 1. And if you just run TrustVisor without performing these security-sensitive operations, there's essentially no performance penalty. There's just a tiny penalty of fractions of a percent for memory virtualization. However, if you do want to invoke this SSL module, and which then performs these signatures, there's about a 10% overhead for setting up these connections. And this is very low. Flickr will be at much lower, more around 50% overhead rather than just 10. There's been a lot of related work in this area. However, I'm not going to address most of this unless people really would like to hear more clarifications. But essentially, a lot of this work used very specialized, either specialized hardware or uses specialized operating system. And the main property we want to provide here is to enable execution with commodity operating systems on commodity hardware, but still obtain very strong security properties for these type of operations. So, in conclusion, we now looked at the properties that trustworthy computing can provide. We saw that we get fundamentally new ways for building these secure applications, because you can build systems that are robust even against a malicious administrator, which is a very powerful property. So you also then get very strong protections against malicious code that can guard the secrecy of your data, even again if your OS is malicious. So these mechanisms are actually surprisingly easy to use. We provide Flickr free to anyone who wants to use it, and we have to build the whole execution environment that can operate with Windows or Linux on AMD or Intel processors. And so you can write your applications using this Flickr code that then executes your security-sensitive code in isolation from all the malice on these systems. So now you can take these mechanisms and hopefully build secure systems that you can use in practice. And we've been building a lot of different systems that provide properties to the human user as well as in the context of cloud computing. You can use the same techniques to verify that your cloud provider is performing the correct operations. All right, so I hope I didn't go over too much, but if people have some specific questions, I'll be happy to answer. So thank you for your attention.